In this section we begin to work with definite integrals. The definite integrals have these limits of integration. For example, in problem number 5, from 0 to 2. And those are x values. And all that means is that we're looking for the area under the curve of the function y equals 6x from x equals 0 to x equals 2. And just so we understand what it is that we're trying to accomplish here algebraically, let's start with a picture of it. So I'm going to use the graphing calculator. I'm going to go into y equals, and I'm going to set up my function up, y equals 6x. Right. Then, in this case, I'm going to set my window because I know that I'm not going to be able to see everything that I want. My x values, I'm going to let go from -5 to +5 by 1s, and my y values from -5 up to 20, let's say by 2s. And then I'm going to go ahead and graph the function, and you can see that there is the graph of y equals 6x, and I want the area under the curve from x equals 0 to x equals 2. Now you may be able to see that that forms a triangular region there. And so we could figure out the area without calculus even. That would be a base of 2 and a height of 12. And so that would give me 2 times 12, which is 24, divided by 2, which is 12. But we're going to use the calculator to figure that out for us. So I do second calc. You see option number 7 there. And the lower limit is 0. The upper limit is 2. And we get the area between the curve and the x-axis of 12. So we're going to take that, and now we're going to show how we would find this algebraically, which is really what has to be done in this particular section. We're looking at the algebraic method of finding the area between a curve and the x-axis. So I'll move the calculator out of the way and we'll get started. So this process of finding the area between a curve and the x-axis has to do with antiderivatives. And so we start with integral from 0 to 2 of 6x dx. Now what we want to do is we want to find the antiderivative of that integrand, and we call 6x between the integration symbol and the variable of integration. We call that the integrand. And so the antiderivative of 6x is 6x squared over 2, which is 3x squared. I'm going to put that in brackets. We've already found the antiderivative, so I don't want to use the integration symbol and the dx anymore. And instead, I'm going to move my limits of integration over to the right. And what I want to do now is I want to find the antiderivative of 6x evaluated at the upper limit. So that would be 3 times 2 squared, and subtract from that the antiderivative evaluated at the lower limit. And so we end up with 2 squared is 4 times 3 is 12. 12 minus 0 is equal to 12. And so this is the method, which is part of the fundamental theorem of calculus, that we're going to use to find antiderivatives. Sorry, to evaluate definite integrals by using antiderivatives. Now that formula is the integral from a to b, where a to b are x values of f of x of some function. And actually it might be easier if we think of that integrand as a derivative. If we think of it as a derivative, then the notation is a little bit easier to work with. So we want the antiderivative of f prime of x, which is just f of x, evaluated at b minus the antiderivative evaluated at a. And so that's how we find the area between a derivative curve, or a rate of change curve, and the x-axis between two x values. All right, let's go on to the next one. So in number 7, it's very similar, only we have two terms in the integrand, 2x and minus 1. And we're simply going to apply the properties of definite integrals, which say that the integral of a sum or difference is just the sum or difference of the individual integrals. So what that means for us is we're simply going to take the antiderivative of each term. So we start off with integral from -1 to 0 of 2x minus 1 dx. So the antiderivative of 2x is going to be 2x squared over 2, which is simply x squared. And I'm going to put that in brackets. And the antiderivative of 1 is simply x. And we want that from -1 to 0. And so I am going to evaluate the antiderivative at the upper limit, which we can see pretty clearly that that's going to be 0, minus the antiderivative evaluated at the lower limit. And you really want to be careful with your signs in all of this process here, especially when we have negatives the way we do here. So -1 squared is +1, minus -1 is +2, but then we still have the minus sign on the outside, so that should give us a -2. And we can verify that using our graphing calculator. So we'll start out putting the function in here, which is 2x minus 1. 2x minus 1, and I'm simply going to set the window to be standard this time, and you can see there that the area is going to happen under the curve this time, so below the x-axis I mean. So it's always the area between the curve and the x-axis, whether that's above the x-axis or below the x-axis. So we're still going to use option 7. The lower limit is -1. The upper limit is 0, and so you see we have an area under the curve of 2, which gives us an integral of -2. The area is always positive, but integrals can be negative if the area is below the curve, is below the x-axis. Okay, the next example, number 9. We want the integral from -1 to +1 of t squared minus 2 dt. And so the antiderivative of t squared is t to the third over 3. Again, I'm putting this in brackets. 1/3 of t cubed minus 2t. And we want this from -1 to +1. So once we take the antiderivative, we're not using the integration symbol s and the dt anymore. We put our result, our antiderivative, in square brackets and move the limits of integration over to the right side. And then we simply want to evaluate the antiderivative at the upper limit minus evaluate the derivative at the lower limit. So let's see what that comes out to be. At the upper limit, it's 1/3 times 1 to the third, which is just 1/3, minus 2 times 1, or minus 2. And then we have 1/3 times -1/3 to the third, and -1/3 to the third is -1. So that's going to give us a -1/3 there, minus 2 times -1, or plus 2. All right, so then you simply have to work out the arithmetic of this. 1/3 minus 2/3 is, so that gives us a value of -3 1/3, or -10/3. So let's use the graphing calculator to show what's happening with this one. So we start by putting our function in, y equals x squared minus 2, and in this case I have my window set from -3 to +3 by 1s, and the y's from -3 to +3 by 1s also. And I'm going to simply go over and graph. So I have this already set up here. If you ever need to clear the integral or the shaded region off, all you have to do is go to Second, Program, which is the draw function, and hit option 1, which is clear draw, and so that will remove any shading that you put in. Alright, so now we want to go to second, trace, which is our calc function. Option number 7, find an integral from negative 1 to from negative, so I have to put a negative symbol there, not the minus symbol, negative 1 to positive 1. And that shades in, and you can see that's negative 3 1/3 or negative 10/3. So that'll do it for that example. Now what's unique about this example is that all of the area is below the x-axis. So we find the area between the curve and the x-axis between negative 1, x equals negative 1, and x equals positive 1, and the entire thing is going to be negative. So we've seen examples of where area is above the x-axis, where area is below the x-axis. In the next example, what we want to do is to do some rewriting before we begin to evaluate the integral. So we have an integral from 0 to 1 of 2t minus 1 quantity squared dt. And the first thing that we want to do is to just expand that out. We haven't learned a rule for function composition of integrals yet. We'll get to that in the next section. So we have from 0 to 1 and expanded out, 2t minus 1 quantity squared is 4t squared. Then minus 4t and plus 1. Alright, so once we have that, we're able to now begin to find the antiderivative. The antiderivative of that is going to be 4t to the third over 3, or 4/3 t cubed. Again, I'm going to put that in a square bracket, minus 4t squared over 2, which is minus 2t squared, and then plus 1, which is going to be plus t. We put our limits of integration on the outside, and we're ready to begin to evaluate that. So at 1, I'm going to get 4/3 minus 2 plus 1, and then at 0 everything goes away, so it's 0 minus 0 minus 0, and we end up with 4/3 minus 1, which should give us a value of 1/3. And we'll bring in the calculator to verify that. And so we start with 2x minus 1 quantity squared, and perhaps our window for the last one will be fine. It's from negative 3 to positive 3 for x's, negative 3 to positive 3 for y's, and we'll go ahead and graph this. And we want our limits of integration to be from 0 to positive 1. So we do second trace, option number 7, 0 to positive 1, and we get 1/3 as the area between the curve and the x-axis there underneath that quadratic. Alright, let's see if we can get these next two in under 15 minutes here. So we are from 1 to 2, and I'm going to do a rewrite here. 3x to the negative second, and then minus 1 dx. So the antiderivative of 3x to the negative second, we're going to increase by 1, so we'll get 3x to the negative 1 over negative 1, which is negative 3x to the negative first power minus x. And that's from 1 to 2. Alright, so the x to the negative 1 is simply 1 over x. So we have, evaluating at x equals 2, negative 3 over 2, then minus 2, and minus negative 3 over 1, so that's a negative 3 minus 1. And since we're going to run out of time on this, I show you my calculations and then the graphing calculator solution to this. You can pause the video and